Greetings, friends, fellow Earthlings, and if you're anything like me, maybe those who are anxiously awaiting samples to be returned from Mars to Earth. Welcome to Ask An Astrobiologist, the show that celebrates the science and celebrates the scientists involved in our quest to understand the nature of life. I'm your host, Dr. Graham, the cosmobiologist Lau, and we're brought to you by the NASA Astrobiology Program and SegaNet.org. As always, we want to thank all of you out there who watch our show, both during the live stream, asking questions in the chat on YouTube, who ask questions of our guests on Twitter using the hashtag AskAstroBio, as well as those of you who watch the show after it's aired. I try my best to come in and answer questions when possible on YouTube. So if you're watching this after the live stream, I will try to answer your questions there if I can as well. Today's episode is going to be incredible. If you know me, you know that I absolutely love rocks from space and what they can teach us about our place in the universe. Today, we have an expert in planetary science, isotope geochemistry, meteoritics, and sample return to Earth joining us for the show. Dr. Meenakshi Wadhwa is a professor and the director of the School of Earth and Space Exploration at Arizona State University. She earned her BS and MS degrees in geology from Punjab University and then continued her studies in earth and planetary sciences, earning her PhD in 1994 from Washington University in St. Louis. Dr. Wadhwa is a planetary scientist and isotope geochemist interested in timescales and processes involved in the formation and evolution of the solar system and our planets. And she was also a recent keynote speaker at the Astrobiology Science Conference, which I heard her keynote talk, and I thought it was incredible. I knew that I wanted to have her on the show to talk to all of us about her research. Beyond being an expert in planetary materials like meteorites, Minnie is also the principal scientist for NASA's Mars Sample Return Program. Dr. Wadhwa, thank you for joining us, and welcome to Ask an Astrobiologist.
Oh, thank you so much, Graham. This is a real pleasure to be here.
Awesome. And like I said, so we did talk before the show. I'm so excited for all the things you have to share with our audience. There's already some questions coming in from the YouTube chat. But I want to speak with you first a little bit about your life, your career, your research. And the one place I love to start off with all of our guests is hearing about your origin story. What got you interested in pursuing the path in the sciences that you're on now?
Well, so I've always been kind of interested in the natural world around me. And I think all kids are at some level, fascinated by insects, fascinated by rocks, that kind of thing. And I was no different, but I kind of remember sort of one moment, though, in growing up, when I kind of realized that this is what I want, I wanted to be a scientist in a sense. I'm not sure I knew the word scientist at the time, but that's kind of what felt right. I remember, probably I was 7 or 8 years old, and in class, my teacher was talking about, respiration and how human beings, breathe in oxygen, let out carbon dioxide. And, this is fascinating. And then, after a few minutes of thinking about this, I was like, oh my God, there's all these human beings on Earth, and we're going to be breathing in oxygen, letting out carbon dioxide. And so we're going to be running out of oxygen pretty soon. And I was like super worried. I talked to my mom that evening, and she was like, well, yeah, what's wrong? You're worried. I was like, well, I think we're going to be all extinct soon. And she's like, oh no, there's all these cycles in nature that, keep things in balance. And yeah, there's, plants do the opposite to photosynthesis. And so all of that. And I was like, oh, wow, there's so much that I don't know and understand, and there's so much to learn. And so I just kind of remember sort of thinking, I'd love to be able to figure out some of these things about our natural world. And of course, as it turns out, of course, we are worried about the levels of CO2 in our atmosphere. And so it wasn't that far off, I guess.
I love it. It's such a cool story, too. Like this early wondering of what's going to happen to us, breathing in oxygen, breathing out CO2, and then making those larger connections to our planet and how life is so connected. We share this one beautiful biosphere, and it's the only place we know of so far that has life. But many of us wonder, and looking at planetary materials from other worlds, meteorites and sample return, if we can actually find signs of life out there. So at what point in your career, you started off studying geology as an undergraduate student and then went into earth and planetary sciences. At what part in your career did you really decide that studying planetary materials to understand the history of our solar system and the history of planets was really your thing?
Yeah, so I went into grad school, and maybe some of the students can relate to this. Starting out grad school, not really knowing exactly what part of planetary science I wanted to really focus in. I had my undergraduate degree in geology, and I loved rocks, and really, I felt like if we could apply the same kinds of things that we apply to Earth rocks to try to do the same kinds of things with samples from the moon or from Mars, and just the thought of being somewhat of I guess, vicariously a geologist on another planet, a geologist on Mars. I mean, that's really what fascinated me, right? And so, but I didn't know how to make that happen. I didn't even know that we had, hundreds of pounds of, lunar rocks from the Apollo missions at the time when I started out. And so it was only, when I got to Washington University and I started talking to a number of the faculty. And the good thing was, of course, there were a number of people that were doing all different kinds of things in planetary science. And I was talking to them about, whether I wanted to do more remote sensing of planets or what are, different kinds of things. And then one of the professors, her name was Ghislaine Crozaz, and she was actually one of the few women planetary scientists at the time. Not very many of them, actually. And so she asked me, hey, do you want to look at these meteorites from Mars? And I was like, what? There's meteorites from Mars? And that was like a mind-blowing kind of experience for me because, I looked at a thin section of this rock and, it just looked so familiar, like Earth rocks that I've seen before, magmatic, igneous rocks. But it formed on another planet and it could tell us something about the geology of another planet. And so that was like, that aha moment. I was like, gosh, I can be a geologist on Mars in a way, right? And so that's kind of what got me hooked into sort of studying planetary materials, because it just seemed like the skills that I'd learned for studying geology on the Earth, I could apply those same skills to understanding something about the geology of Mars.
Oh, I love that so much. And I want to step back just for a moment because you mentioned something really important there, that there weren't many women at all in planetary science. And so you had a woman as a mentor and someone who could guide you. I wonder if you can speak to the value, not just of representation, but also of mentorship in your career.
Yeah, I mean, Ghislaine, she's somebody that I still am in, contact with, and she's been a, lifelong mentor and friend for me. And I think it was just so important to be able to see somebody in that role, so I could actually see a path for myself in this career. But even before I joined WashU, though, I remember contacting her, and at that time you had to write letters, and I remember saying, hey, dear Professor Crozaz, and assuming that it was a man, because I did not know any better in my undergraduate career. There were not any women professors. There were not actually even hardly any women students alongside me. And so, it changed everything for me. I mean, I knew it was possible for me to be a scientist in this particular field because I saw Ghislaine doing it, So yeah, it's so important.
Oh, that's wonderful. And that reminds me of a personal story. A friend of mine, she's a wonderful explorer and she's done education around the world. And she was going on a trip to teach astrobiology and planetary science to a girls' school in Bangladesh. And I had been talking with her about possibly going along. And I remember she reached out and she said, actually, I don't think you should come. Because she had noticed in her previous visit that when she was talking with these young girls, they were all so excited to share their knowledge and to ask questions. And then the principal, an older man, walked into the room and all the girls sat up straight and put their hands down and were very quiet after that. And I think it's so important for young women around the world to experience representation, to see women doing incredible things and to feel like they are part of this grand journey of being human with all of us.
Exactly.
So I'm so glad that, that to hear that there's more representation now, but we still have a lot more work to do.
We do.
And I'm so glad that you were inspired to continue in your realm and do the work that you've done. Before we talk about meteorites, which I'm kind of bubbling right now, I feel like my skin getting all excited to talk about meteorites because I love space rocks so much. We did a poll through the NASA AstroBio Twitter account asking people, we gave them 4 options of possible meteorites and asked which were their favorite. We gave them ALH 84001, the Allen Hills meteorite that famously in 1996 was a potential signs of life were announced. the Black Beauty, the other weird meteorite from
Yes.
Mars, the Murchison meteorite, which we've now found dozens of organics, amino acids inside of the Murchison meteorite, and the Chelyabinsk meteorite. I thought we'd throw one in just kind of for fun to see if people were thinking more about like more recent things they've heard of, because Chelyabinsk in 2013 was a fireball that exploded over Chelyabinsk in Russia. And people actually, they picked Chelyabinsk as their favorite one. And Murchison actually got the least amount of love, which kind of hurt my heart a little bit because I love it so much. And as an astrobiologist, I think it's so important. Of those four, which do you think is the coolest?
Oh my God. That's like asking who's my favorite child, right? I mean, that's a tough one. I love them all, but I would say probably Black Beauty. Black Beauty, because that's a really fascinating meteorite, by the way. The Martian meteorites that we have, they're all different kinds. There are about 130 or so that we know of. But this is like one of a kind, unique Mars meteorite, because it's actually an agglomeration of all different kinds of rocks. Most of the other Martian meteorites are igneous rocks coming from one single rock. And this one's sort of like a mishmash. And the other thing that's really, a couple of things that are really fascinating about it. It has the most amount of total water, close to 1% almost, which is a ton compared to what's in the other Mars meteorites, which are, in parts per million or something like that, total abundance. And the other one is that its bulk composition is actually very similar to the compositions that the Mars rovers are measuring for the surface rocks on Mars. The other Mars meteorites that we know of, for some strange reason, they're not exactly, analogous or in composition to what we're seeing from the rovers. But this particular rock, it's bang on, the same kinds of composition range that you're seeing from the rovers. And so in a sense, it represents the average composition of the Mars crust in a much sort of more representative way than the other Mars meteorites do. So it's I think it's just a fascinating, beautiful rock. I don't know if you've seen pictures of it, but it's kind of a gorgeous looking rock as well.
Yeah, absolutely. I've seen pictures. I haven't seen it, but I've seen pictures. And yeah, it's very beautiful. It's a very cool rock. I have some meteorites of my own. I love them all. So I can understand your hesitancy to pick a favorite, but Black Beauty is a very cool rock. So I'd love to hear a little bit about meteorites. You've gone out to the field to collect meteorites. You've gone to Antarctica to collect meteorites. I'd love to hear a bit about what it's like to go out and collect these rocks and bring them back to the lab and then do, isotope cosmochemistry on them to try to understand their history.
Yeah, no, I tell you, I mean, Antarctica is one of those places where you cannot really describe it adequately, nor can you actually photograph it and sort of convey the wonder of being in that place through photographs or even, video footage, just because when you're down there and you're out in the field and you're in this space. And by the way, the field trips that we went on, you go there during the austral summer, which is 24 hours of daylight. And it's just an incredible thing. I mean, it takes your body a while to get used to that 24 hours of daylight. But then after a while, you can actually just, depending on, where the sun is relative to the horizon, you can tell kind of what time of day it is or night it is. and just sort of the field camp where we camped, just the isolation of it. We're hundreds of miles from any kind of, occupied areas, from McMurdo Station or from Palmer Station, hundreds of miles from that. Out on this kind of ice that's miles thick, and there's no wildlife whatsoever really there. And you're there with these, 5 other people that you're really dependent on for your existence. Really, you're dependent on each other, and it's like the most beautiful place in the world, I think. But then, hunting for meteorites there, I mean, that's just, again, a mind-blowing experience. I mean, for me, I studied meteorites now for all of my career, but that first experience of actually finding a meteorite out in the field and just actually sort of recognizing that, hey, there's actually a mechanism that happens here in Antarctica that actually concentrates these meteorites so that you can find sometimes hundreds of meteorites in an area, maybe, the size of a football field. I mean, it's just incredible. And so even though your mind understands that, it's still like amazing to find these rocks sitting on the ice and collecting them and bringing them back. And so, I had the good fortune of actually going down a couple of times as part of the Antarctic Search for Meteorites program. I went once as a graduate student, and then I went again just about a decade ago now. So it's been a few years, but what an amazing experience.
Oh, that's so cool. I'm super jealous. I have been to the Arctic. I've been to a place above the Arctic Circle where the sun never sets. And it was indeed bizarre just to have the sun just do a big circle and never have a night. I was only there for 2 weeks, so I never really had a chance to get very acclimated to it. But field work can be dangerous. Those who know me know that we also had a potential near-death experience when we were in the Arctic doing our research on a glacier. And as I understand it, you also had a rather terrible experience doing some field work back in 2017 in Iceland. Would you mind sharing that story with our audience?
Yeah, that was a pretty scary experience. But I mean, so Iceland, of course, I mean, the reason I was in Iceland was to collect some Mars analog samples. I have a project where we're trying to understand the role of water in igneous rocks. And so Icelandic rocks are really kind of perfect for looking at some of these comparisons. And so we were out there, this was day 3 of the field trip, and I had a colleague from the University of Iceland who was a geologist who was sort of helping us collect some of these samples. And we were in actually quite a remote part of Iceland, several hundred miles from Reykjavik. And we had a lunch stop, and we're just sort of getting going after that. And normally, I mean, it's in this remote part of Iceland where you hardly ever see any cars at all. But, getting out of the lunch spot, there were a number of other cars that were getting out. And my colleague who was driving the car, he tried to sort of quickly overtake a series of cars. And one of those cars just pulled out into our lane and sideswiped us. And it's, our vehicle just went kind of end over end, basically, rolled over. I literally was tossed out from the vehicle, something like 30 feet away from the vehicle. And it was, I don't remember any of it, actually. It's completely gone from my memory banks, but it was, I woke up in the emergency room not knowing kind of what happened and had a series of really kind of traumatic injuries, most of them on my left side, broken pelvis and fractures, my shoulder and arm and all of that. And as a result of that, I mean, I had about a year of recovery after that. I was in a wheelchair for about 4 months and lots of physical therapy. But it was, what it made clear to me, I had a lot of time to think. And I had a lot of time to sort of think about, what I wanted to do with my life, and I realized that, hey, I better, do things that really kind of are going to be meaningful and, that I'm really passionate about and really care about. And so it's really kind of, I think in some ways helped me to kind of redefine kind of my path. And I realized that, hey, I wanted to be, I'm excited to be part of education, but I want to make education opportunities available to many more, students out there. And so that's part of why I actually, I became director of the school where I am at Arizona State after that, because I decided that's kind of the path that I wanted to take, not just focusing just on my research, but also trying to make opportunities in education more available.
Oh, that's beautiful, and thank you for sharing that with us. And I'm glad that that you survived. I mean, obviously you're here with us, and to hear that it's such a remarkable time for you in your life, and it kind of gives you that pivot to think a bit more about your own impacts in the world. One reason I wanted to bring that story out is because we all have our stories, and I think a lot of people think scientists they just wear lab coats all day and they're in the lab, and they don't realize that we're out in the field, we're on computers, we're of all different backgrounds, and we also have our own stories, our own histories, and some of those histories have rocky starts and fits and jumps and changes along the way. Much like when we look at a meteorite or a rock from space, it can tell us about the history of our solar system, the history of planets. And I know that you've been involved a lot in early solar system work and the history of the worlds of our solar system as well. I wonder if you can make the connection for us then from the work you've done in meteorites and the early solar system and things like that to then getting involved in sample return missions.
Yeah, it's a very natural connection, actually, because, meteorites, most of them actually represent pieces of asteroids. And so in a sense, what you've got with meteorites are a very cheap way of doing sample return because they actually come to us. And so, the samples that we have of Mars, the Martian meteorites, we're spending billions of dollars to actually go to Mars and get those samples back now, because there is actually some value to doing that, because meteorites, of course, they're wonderful and they come to us free, but they're not I would say, a non-biased sample of Mars. And they've been through a lot. They had this huge impact on Mars that ejected them. They went through these shock processes, during that process. And then they've been sitting around on the Earth for a long time, exchanging with the Earth's environment. And so things change as a result of that. And so we want sample return because of those factors, right? But in a sense, that connection is very much there. I want to be able to study materials from places in our solar system that, hopefully we can go and actually get them with spacecraft. But meteorites kind of extend that possibility to a lot of to places and times that we otherwise, can't have a very hard time sampling otherwise. And so that connection was kind of, obviously from the very beginning. When I started studying these Martian meteorites, I really was at that time, I was thinking, hey, wouldn't it be great if we could actually go to Mars and pick up some samples that we understand the geologic context of, and then, bring them back and study them in their pristine condition. And, I've dreamed of sample return, since that time. And it's always been sometime in the future, 10, 15 years down in the future. And that horizon kept moving back. And then finally, we're at this point today where it's all coming together, and there's a timeline. We're in plans of, basically making plans for getting those samples back. And I can actually see it happening now, and it feels real. So this is a really super exciting time.
That is so exciting.
Yeah. And Mars sample return is not the only one that I'm involved in. Of course, I'm actually part of the science team for the Hayabusa 2, Japanese space mission, space agency's mission to an asteroid called Ryugu. And we're analyzing actually pieces of that asteroid in my laboratory right now, and learning things about our early solar system from that. So wonderful. I think this is really the golden age of sample return at this point, and so exciting. Really excited for actually students just starting out now, who will really be benefiting from all of what we're going to do in the future with this, and they'll be engaged in analysis of these materials.
Absolutely. There could be a student watching right now who might end up analyzing Mars sample return materials, or even some of these materials from Ryugu, or samples being brought back right now from OSIRIS-REx. We've done some sample returns. We have some asteroidal materials. We brought some cometary dust back.
Yes.
We have the Apollo samples we brought back. So there's already stuff that we have. But of course, we always want more. And so this is the very first time we are going to do a Mars sample return in this current architecture. I wonder, so maybe our audience doesn't really quite know the whole structure right now of MSR. I wonder if you could walk us through Mars sample return and what that's going to look like in the coming decade or so.
Yeah, so, we are in what we call phase A for Mars sample return mission. And so the plans are still in formulation. So you got to keep that in mind. I think the architecture is not completely determined at this stage. But as we are planning at the current time, what the plans involve are two components to the mission. One is going to be an Earth return orbiter, which is going to be, and actually this is a partnership, I should say, between NASA and the European Space Agency. And so there's parts of it that ESA is going to be doing, parts of it that NASA is going to be doing. And so there's one component, or one mission launch, actually, that's going to involve an Earth return orbiter, which is going to go to Mars, and it's going to orbit around Mars. And it'll become important as I explain this a little better. But the second launch is actually going to be a sample retrieval lander. And it could be one or it could be two landers. And they are going to take down to the surface of Mars, they're going to take a rocket that's going to then launch off the surface of Mars and bring back the samples that are collected in a little canister. And so this is going to be the first time ever that we're going to launch from another planet. So it's historic from that perspective. And then the launch is going to then take this sample canister from Mars. It's going to orbit Mars and going to be captured by this Earth return orbiter. And then there's going to be an Earth entry system that's going to basically bring back those samples back to Earth. And so it's a really complicated mission in the sense that there's multiple components to it. There's obviously partnerships, between NASA and ESA. There's a number of different NASA centers that are contributing various parts to the different components of this mission. And so it's going to be one of the most ambitious things that NASA has done in a long time. And I'm just so excited to be part of it.
It's so groovy. Yeah, I mean, we've been doing all these cool things. The engineers at JPL are just doing so many cool things with how we land the rovers and all this stuff. But this is a huge structure, a huge architecture of how we have to do these different launches and get these samples back and then start to analyze the samples as well. But there is so much we can do with our high precision instruments here on Earth. And when we have those samples in hand, I think it's always important for people out there to remember that we can do so much more science with these samples, and we have them in hand than we can right now with our rovers on Mars.
Exactly. I mean, you've got instruments like these synchrotrons that are about, several city blocks across. I mean, you can never take those on spacecraft and use them to analyze material. So it'll be, we'll be able to analyze these samples with the best and most, state-of-the-art technologies that are available here on Earth. And the wonderful thing about it is, the advantage of time, right? And once you bring these things back, you can actually wait to develop some technologies that, you may not have. I mean, and we are going to actually analyze these materials with technologies that don't exist today, but will in the future, right? And so, there'll be questions that we'll ask that we can't even think of right now. So, I mean, just the powerful nature of sample return is just that you have these materials back and they'll be available for generations to come. The Apollo samples, for example, I mean, they came back in the late 60s, but even last year, we opened up a sample tube that had been sealed for 50 years, and there's new science being done on those materials. I mean, learning new things, so it'll be an incredible gift to bring these materials back.
Yeah, definitely. I've been fortunate. I've done X-ray spectroscopy at 3 different synchrotrons in my own life, and you're right. These are gigantic facilities, mega facilities that we're speeding electrons close to the speed of light around these huge rings that it can take you 15 minutes or over an hour to walk around them. Some of them even have like tricycles and stuff for you to go around the rings with.
Yeah, and the amazing thing is, of course, I mean, the power of that is that you can actually study these samples almost at the atomic scale, right? And there's no hope of actually doing that remotely on other planets. We have to bring them back to be able to study them in that detail. And you need that really, to be able to really address that question of, is there evidence of past life in these rocks? I mean, you're going to need that, level of precision and level of spatial resolution to be able to address those types of important questions.
Absolutely. I do want to open it to our audience Q&A here very soon. So I see a lot of questions rolling in right now from my team. From those who are watching right now, the live stream on YouTube are asking questions in the chat. So please keep asking questions. We'll get to them very soon, I promise. But now we have our FTL segment, our faster than light. Rapid fire segment. So just, rather short answers, but if you don't mind, these are some just interesting things that might draw more out about your interest in your career. First one comes from me specifically. What stories, what kinds of fiction stories, nonfiction stories, human stories have inspired you to want to explore more about the universe?
Gosh, so I can think of maybe 2. So one human story that really inspired me is Shackleton's story, the Antarctic, exploration, and Shackleton just, one of my big time heroes. I think just his leadership style and just his exploration of the Antarctic and how he kind of kept his team together under really hardship conditions. The book Endurance, I think, actually really captures that so well. And I was just, it's one of the most inspirational things to me personally, I think. He's a real hero in many ways for leadership and exploration. And then the other thing I think that really affected me as a child actually was watching, Jacques Cousteau's documentaries and exploring the undersea world. And that just was incredibly sort of fascinating for me. And yeah.
Absolutely. That's so cool. If you could go back in time to the beginning of your career and give yourself some advice, what would you say?
So I would tell my sort of younger self that you should really appreciate the moment, live in the moment more instead of always focusing forward and planning for the future and what you might do. I think just enjoying your time where you are, what you're doing, I think that's so important. And that's something actually that I think I could benefit from even today, that a piece of advice. And then I think the other thing I would say is take more risks, take more chances, put yourself outside your comfort zone every once in a while. I think that's when we actually learn the most, is when we do that.
Absolutely. What's something that really excites you right now about the future of planetary science and astrobiology?
Gosh, I think, like I said, the golden age of sample return, right? We're looking forward to all these materials that are going to be coming back. We're going to have the OSIRIS-REx materials coming back next year. We're planning for, these Artemis missions that are going to bring back all these samples of the moon in the near future. And then, of course, Mars sample return. So, I'm super excited about that for the next, decade or two. We're going to have some fantastic materials coming back.
Absolutely. So we mentioned earlier, you're a professor and the director of CC. You informed me earlier before the show, I was pronouncing it wrong for years, the School of Earth and Space Exploration at ASU. Yeah. What is your favorite part of your job?
Gosh, what I love about my job is that no single day is this, it's not the same as any other day. Everything, every day is different, and there's different challenges. There's always something that's new and different to do. And of course, science is part of that. And I love the mentoring part of it as well. That's such an important part, I think, for all of us, is to sort of give back to sort of the growth of our community and our field. And really, I want to be able to provide the opportunities that I've had to others. So, yeah.
Very cool. And this is a fun question. What is an unbelievable science fact that still blows your mind?
So an unbelievable science fact for myself, actually, and I can't believe I actually participated in some of the findings for that, is just the age of our solar system, right? 4.5678 billion years. We know that to an incredible level of precision. And just to think about that, the context of that, if you think about, to wrap your mind around that big a number, it's hard even for somebody who studies it, on a day-to-day basis, to even do that. So if you're thinking about the length of your arm, that's about the whole of human, Earth history or the solar system history. And you were basically, if you were to take a nail file and rub it against your nail, you would remove all of human history, right? So that's the kind of scale that you're talking about. It just blows my mind, just thinking about, what the age of our solar system is. And when life originated, actually, is a very small fraction of that time. So, I think just geologic time scales, and that's kind of the most incredible thing to me.
Oh, I love it. It's so mind-blowing, right? Like, we evolved to think on scales of seconds and minutes and length scales of a meter to 3 meters, or a centimeter, to think of things in such huge scales, both really long periods of time and super short periods of time. Just, it is very staggering. So I love that a lot. I do want to jump now to our audience Q&A, since I see we have a bunch of questions to get to. The first question actually came into us via Twitter a couple of days ago. And at first, I misunderstood the person who was asking. This is user J Van Evert at Jan_1 on Twitter. They wanted to know why only rock samples are being collected so far, and why for Mars some scientists say radiation will kill all life to a depth of 3 meters. Now, to be fair, I responded. I thought they meant, why are we only collecting rock and not like water or ice? And obviously, if we can get to Europa or Enceladus and fly through the plumes and collect some material and bring it back, that'd be fantastic. But their real question about the collection was, why aren't we collecting regolith from Mars? Like, why are we looking for solid rock samples in those cache tubes and not like scooping up some of the surface material?
I think actually the plan is to collect some of that regolith material. So there is interest in collecting regolith as well. And there's lots that you can learn from studying that type of material versus the rock cores as well. So yeah, absolutely. I think, what we're trying to do, what we're going to bring back is going to be rocks. It's going to be regolith. There's also going to be Mars atmosphere that we're going to bring back. So yeah, all different kinds of stuff.
Yeah, and so another good question. So the second part of their question then was about depth. So the surface of Mars we know is a lot of radiation coming in compared to the surface of the Earth, and it's a highly oxidizing environment. And so a lot of people have said if we're going to find biosignatures, we need to dig deep. Now, obviously, these samples from Perseverance aren't going to be very deep samples. So do we have an issue then with the quality or potential for biosignatures in the samples from Perseverance?
So I think there's what I want to clarify here is that the goal for Perseverance and the goal of investigating this particular region that Perseverance is in, this delta region in Jezero crater, is not to look for extant life so much as evidence of past life. The probability of extant life is very, 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 very low in this particular region, So what we're hoping to do is, in the past, we think that this was an environment that was habitable in the ancient history of Mars. And so the environment then was very different. There was possibly liquid water on the surface. There was a thicker atmosphere, perhaps. It was warmer, wetter. And that's when, some of these rocks were likely deposited. And so what we're looking for really is not evidence of extant life. And sure, yeah, absolutely. I mean, in the current environment there is completely inhospitable. But what we're hoping to find is biosignatures that point to evidence of ancient life. And yeah, I mean, I think we're going to the right places there to look for that. And we hope to find it. I don't think we need to, necessarily go down very deep to look for ancient evidence. So.
Very cool. I agree entirely. There's still so much value in those samples. Our next question comes to us from Dr. Jim Pass, who leads the Astrosociology Research Institute. He always wants to ask questions that are related to sociology and human behavior in our research. And so Jim has said the Mars Sample Return Program represents a highly anticipated next step in the search for extraterrestrial life. He would like to know your thoughts on how social scientists, and maybe even others in the humanities, can participate, including putting these findings into the proper context for human life.
Yeah, no, I completely agree. I mean, this is, one of humanity's biggest questions, I think, is, are we alone in the universe? Did life originate elsewhere in our solar system? Did it, originate elsewhere in the universe? And these are big questions that I think it's not just scientists that grapple with that. It's all of humanity and certainly the social sciences. And I think we're going to need the participation and the perspectives from social science to really help us frame, whatever that we find, for us human beings to really kind of frame what it means to be alive on this planet. As humans, we need to sort of understand that and to put that in the right framework. And from that perspective, I think, whatever the answer that we get, whether it's yes or no, I think it's going to have a huge impact on what, be human beings, how we perceive ourselves and our place in the universe, right? And so I think there is a huge role for social sciences to play. And in fact, for everyone, all of humanity to really sort of be able to participate in that exploration and that sort of answering that question. So, yeah. I think it's a great question.
Yeah. Reminds me of a Star Trek Next Generation episode called Samaritan Snare, where Captain Picard is basically explaining that, anyone can learn, celestial mechanics and how to pilot a starship. But if you study history and philosophy, theater, art, then it makes everything else make sense.
Yeah, exactly.
We have a couple of clarification questions here about your work. One of them from Sibsankar Palit on YouTube wants to know if you can clarify the difference between astrochemistry and cosmochemistry.
So, it's a fine line there. I think astrochemistry, cosmochemistry probably gets to the same sort of thing. As I look at it, I've always called myself a cosmochemist. What that just means is understanding something about the chemistry of the cosmos. And so astrochemistry is about, similar, I would say, in the sense that it's also getting to the chemistry of this universe and stars and all of that. So, I think it's a fine line there, and I wouldn't put too fine a point on it.
Awesome. Nikki, the science teacher at Teach Astrobio, wants to know, what is the mechanism that concentrates meteorites in Antarctica?
That's a great question, actually. It's it's a fascinating process that we actually don't understand super well. I think we understand more kind of broadly what happens. So as we understand it, there's almost like a conveyor belt-like mechanism that happens in Antarctica. And we actually, I mean, it should operate in similar ways in other places on Earth, like Greenland, but we haven't actually seen meteorites there or found meteorites there in the same kind of abundance or concentrations in Antarctica. But what happens, we think, in Antarctica is, you've got these big ice sheets that are miles thick in some places, and they're actually moving along, basically from the center of the continent out towards the coastlines. They're flowing gradually, these ice sheets. And when they come up against some kind of mountain range or even some kind of subsurface obstruction, the ice tends to move up. And it's also actually at the surface, it's sublimating because you've got these katabatic winds, these gravitationally driven, really, and I've experienced those winds, by the way. They're not fun. They ablate the surface of the ice. And so when meteorites fall over time, they get carried along with these ice sheets until they come up against, basically these areas where the ice is being ablated and it's being exhumed, basically. And they come up and the meteorites come up and they kind of concentrate in some of these areas that are called stramming surfaces. And so they're typically blue ice fields because of the nature of, the way that the ice is moving, and it's very kind of, being ablated away in these zones. So basically that's the mechanism. And, when I actually saw it without my own eyes, standing in a place where I could actually see a number of different meteorites within a small area. I mean, it's just, how incredible is that, And they're not related. They're not part of the same strewn field or anything like that. They're all different meteorites that have sort of accumulated there over time, over hundreds of thousands of years, And it's incredible. I think it's such a gift to be able to go and collect these meteorites every year and find new samples every year. And they've contributed so much to our understanding of the solar system and the universe, actually.
Absolutely. And part of that understanding feeds into our next question then. It's a pretty big question from Rendering Reality 3D Animations, led by Tom Caruso on YouTube. Tom wants to know if you can explain the differences of water distribution early in the formation of the solar system and how those differences impact what we see now.
Yeah, that is a really big question. So, water, of course, I mean, we're interested in it because of the habitability aspect of that, right? But I mean, it's sort of one of those molecules that also, just like any other kind of chemical sort of molecules that are condensing from a cloud of gas and dust, it's going to behave in a way that is geochemically, makes sense in terms of its kind of geochemical behavior, its volatility, and condensation temperature. All of that sort of factors into sort of the initial distribution of water in things that were condensing from that cloud of gas and dust, which is where we started out. As our solar system started out as a parcel of gas and dust that collapsed, and then in the center was the sun, and you had an evolution of temperature and density in the early history of the solar system. And so there was actually what we call a snow line, which is the parts of the solar system that, and it's not sort of a sort of a hard and fast line, right? Because it's actually evolving with time as the solar system is forming, where that line is. But that's the place where liquid water is stable. Actually, it's not the place. It's basically the place where ice condenses from the cloud of gas and dust, and so that will be the snow line. And that evolves with time as the sun is forming, and so what we think is that the inner parts of our solar system were typically hotter at the very beginning, and there was the volatiles were like water were much more depleted in the inner parts and then the outer parts of the solar system, which were cooler. But there was a lot else going on in this early solar system. There's all of these dynamics of things that, the transport of materials from the inner to the outer solar system in jets, perhaps, or just through, turbulence in the disk. And all of these factors actually kind of affect how these things get distributed, and it's rather complicated. But the bottom line is, we found, for example, from the stardust samples, the comet materials that were returned, that there is actually what we'd expected to find there was that maybe it was just an agglomeration of very sort of primitive materials. But what we found is that there's actually stuff in the stardust samples that came from the inner parts of the solar system, meaning that there was this huge, large-scale transport of materials. And so the distribution of water, in the solar system was, generally speaking, I would say that there's likely more water in the outer portions of the solar system as it was forming, where ice condensed. But then things were kind of mixed around, and water evaporated. There was lots going on at the time. Rocky worlds were forming. You had comets crashing into them, maybe bringing in more water from the outer parts to the inner parts. So it's a complex dance, really, that we have to try to understand. And that's part of the fun of really doing that, studying these objects.
Absolutely. There's still so much to learn and so much to piece together about the processes that have occurred through our solar system through time. We're going to shift gears really hard right now. I might start answering this question. I'll see if you'd like to answer it as well. David R. Bunting at DA Bunting has asked if it's probable that the first extraterrestrial life we encounter will be non-biological rather than biological. I'll start by answering that one. So you might have seen a previous episode of the show, David, where I had Dr. Susan Schneider on the show. Dr. Schneider is an expert in the future of the human mind and artificial intelligence, and we talked a lot about post-biological life. So not necessarily non-biological, we use the word post-biological, such that we have an evolution from chemistry through biology as we know it, organic chemistry becoming life. But then we have this transition phase into post-biological life, artificial intelligence, this idea of humans merging with machines and those kinds of things. We don't know what our own future holds. But when it comes to whether or not that's probable, the truth is we don't know. We don't know yet, even if there's other life out there at all. We could be alone. It's kind of sad to say that, but it's possible based on our current knowledge. It does feel, though, that when we start looking out there into the universe, we see all these other worlds, we think of all the potential. It starts to feel like there must be something else. And if there is something else, that makes a lot of us wonder, are post-biological civilizations likely? And it's a very big question. Minnie, I don't know if you want to add on to that or not. That's entirely up to you.
No, I think you said it very well. I don't think I have anything more to add to that.
All right, thank you. So our next question from Ruchira Pal on YouTube. Ruchira wants to know, first they say it's really inspiring to hear from you today.
Oh, that's great.
Ruchira wants to know, would love to learn if there's been any instance that has been particularly challenging for you, yet exciting with respect to your studies.
Yeah, I mean, that's part of what I really enjoy about what I do is that there are lots of challenges. There's analytical challenges. There's, in terms of, every once in a while, there's some really hard problems to try to solve with grappling with the kinds of questions, So some of them, I think the most fun things are ones that you sort of really have to work towards to get to. And so I don't know if there's any particular specific things she had in mind about what kind of challenges, but yeah, I mean, I think the reason why I love what I do is because there's challenge involved. It's not an easy thing to just get from one day to the next. I think, we get to analyze these materials that are really, we have to make the most out of small amounts, and there's limited amounts. And so we have to be very, very careful about how we utilize those samples, and that's part of really what draws me to what I do is the challenge.
Awesome. Our next question is actually a merged question from two of our current viewers. Marina Ripan and Meenakshi Wadhwa asked rather similar questions, and so I'm going to ask both together and let you choose how to answer. First off is, how do we actually know that Mars meteorites came from Mars? And then following on from that is, what are the geological and chemical differences between rocks from Earth and Mars?
Those are great questions, by the way. So it's kind of a fun detective story, really, how we know these meteorites came from Mars. We actually, and it took actually the Viking lander to be there before these rocks were actually definitively, or most sort of as definitively as we can tell without actually having sample returns back, right? The Viking landers were these landers that a couple of them that landed on Mars in the 1970s, and they measured the atmosphere of Mars very well. So we know what the composition is in terms of how much nitrogen, carbon dioxide, some of the noble gases. And so for a long time, there was actually some suggestions by some of the people that were studying these rocks, these Martian meteorites, as we call them. And they found some unusual things in them. They found some minerals that had some water, which, a lot of the other types of meteorites that we were studying were incredibly dry. And then they also found that the ages of some of these meteorites were actually a lot younger than many of the other types of asteroidal meteorites that we were studying, which are closer to the age of the solar system, 4.5 billion years. But these Mars meteorites, some of them were as young as something like 160 million years. That's when the Earth had dinosaurs walking around the surface. So geologically speaking, that's young, right? And so unusual features like that, and people are wondering, how come these rocks are so unusual compared to some of the other meteorites? And some of the brave geologists, among them actually somebody known as, his name is Hap McSween, and he and Ed Stolper at Harvard, they were graduate students at the time. They suggested, this was in the late 70s, that these things may have come from Mars, but we had no definitive evidence. They really stuck their necks out, by the way, to do that. But what happened was that in the early 80s, some of the labs actually studied pieces of these Mars meteorites, actually one particular meteorite that was found in Antarctica, by the way. And they heated it up and they released some gases from these rocks, and they measured the composition of the gas. And that gas matched very well the composition that we knew of the Mars atmosphere. And it's almost like a fingerprint. I mean, that composition is very different, actually, than anything that we know about, but it's very similar to the Mars atmosphere. And that was like a smoking gun, basically, that told us that these meteorites actually came from Mars. So that's how we know. As I said, there's about 130 or so meteorites that we think that are from Mars. We haven't done this kind of gas analysis for all of them, but there are other geochemical signatures that we can match for all of them that basically tell us that they came from the same place. And so that's why we think these are from Mars. And I think, obviously when we bring back Mars samples from the sample return, we'll be able to definitively confirm that when we compare the geochemistry more so. But that's basically the essence of why we think these meteorites came from Mars.
Awesome. I've always had the question, do we have Venusian meteorites, but we just don't have the past knowledge of Venus to know? What do you think of that?
That's a great question. I think, it's much tougher to get things off of the surface of Venus. It's a much bigger planet than Mars. And so gravity well is much, much more to overcome, to get pieces of meteorites. The probability is not zero, but it's much, much smaller than getting Mars meteorites. And of course, you have to also fight the gravity well for the sun, to bring samples from Venus out from Venus towards the Earth, rather than from Mars falling back in towards the sun, I guess. I mean, so you actually have a number of factors. And also, Venus has a much thicker atmosphere than Mars does as well. So just the probability of having Venus samples is very much lower. And same thing actually for Mercury. There's actually been suggestions that maybe we have Mercurian meteorites. It's possible, but I think just getting samples from so close into the sun's gravity well out to where the Earth is a lot less probable than getting Mars samples into Earth. So.
Absolutely. All right, I think we have time for maybe one or two more questions. Let's see. So first, we have a question from Meenakshi Wadhwa, who wants to know what you were studying as an undergraduate in Punjab University, and then how that got you into planetary science and being connected to this realm of astrobiology.
Yeah, so I would say I'm a classically trained geologist, but I had my training in India, where the system of education is a little bit different. It's so I majored in geology and I had minors in physics and chemistry. And those were sort of the areas that I really focused in on. I, studied a lot sedimentology, paleontology, structural geology. We had lots of field work that we did in all different parts of the country, all the way from the Himalayas down to South India, places in South India. So it was a very sort of classical geology training, I would say, but with a lot of physics and chemistry mixed in. And what I found, actually, I was offered a job at the Oil and Natural Gas Commission in India after I finished my degree. And the other option, what I was thinking about, graduate school, and just that dream of wanting to be really, a geologist, but geologist who studies rocks from other places in the solar system, a geologist on Mars, in a sense. That's the dream that actually brought me to graduate school in the U.S., right? And so I kind of wanted to apply the tools and skills that I learned as part of that geology training to other places in the solar system. And that's how I got going in planetary science.
That's awesome. Well, I'm so glad you got going in planetary science and that we've had this opportunity to connect today, to chat, to hear about your research and your experiences, to talk a little bit about meteorites and rocks from space, which are some of my favorite things. Thank you so much for joining us and for sharing your time with our audience.
Well, I'm so pleased to have been able to join here, and loved having the opportunity to answer these great questions.
Yeah, and you had some awesome answers. We'll have a recorded version of this episode as well that will go up online so others can watch later on. If you'd like to learn more about the School of Earth and Space Exploration, CC, at Arizona State University and Dr. Wadhwa's work, you can find that online as well. I do want to give a plug real quick for the most recent version of the Astrobiology Graphic Histories was just released this summer at the Astrobiology Science Conference. And I just recently learned that we now have not only the PDF version of this available online for free, but now we have an EPUB version as well for those who'd like to read the NASA Astrobiology Graphic Histories on their e-reader. So for those of you who want to stay in the loop about NASA astrobiology and the things that we're doing, you can sign up for the newsletter. You'll get the link right now. You can also follow NASA Astrobiology on Twitter at NASA Astrobio. You can follow me at Cosmobiologist. And as always, we're so appreciative of all of you joining us and for learning more about astrobiology, for tuning in, for asking your questions. So as always, stay curious.